welcome once again. This is the lecture number 12 of the deep learning course. In today's session, we are going to talk about how we can initialize the weights of a neural network. So in the last class, we have seen that what do we mean by the big neural networks means when we combine multiple neurons across the layer, and how we can train that. So we have in the last class seen that what is the mathematics and how what is the procedure by which we can find out that what are the appropriate weights along the layers. And today's class we are going to talk about the neural weights, okay, initialization. So what do I mean by this? Actually, the neural weight assignment is this, that you know that if uh, multiple layers are there, and let's assume that you want to find out the weight from here. So how should you initialize the weight? So we are going to see, we in this session we are going to see that what is the problem with the different kind of random weight initialization and etc., and what is suggested, what is the suggested thing into the neural weight assignment. Before starting this, I would also like to bring a very interesting and important point in front of you that we have till now not discussed, that is called the one hot encoding. So today, this is also very much important because whenever you are going to make a neural network based system, you need a kind of encoding. What do I mean by this encoding? So actually what happens, let's assume that you are developing a problem where you have an image, and in the image multiple things could be there. Let's assume that the 5 things are there, and they are cat, dog, bus, plant and apple. Let's assume 5 things are there. So 5 things could be there into this image. You want to build a system that can tell that with the probability, that what is the probability that it is cat, dog, bus, plant or apple, and based on that you can find out that whatever item has the highest probability, you are going to say that this item is there inside your image. So how you generally design this kind of system, you, as we have few minutes talked about, that you are going to deploy a neural network circuit out of that, and to this circuit you are going to feed this image, and at the final layer, at the output layer, that we say that at the output layer there should be neuron, they are going to correspond to each of these categories. So so every neuron is going to be connected with respect to each of these categories. No, I think this, the better would be that you find out there's some kind of encoding on this. So you can tell that let's assume that because I assign some kind of number such that I can say that this is the first item, second item, third item, fourth item, fifth item. Because you know that from output cannot be cat, dog, bus. Output could be only numbers, because we are playing here with the numbers every time we are, even if it's an image, it is actually numbers. You feed the number, you get the number. However, our understanding is this, that it is cat, dog, bus, plant, and apple. But for the computer, it is not like that. For the computer, it is going to be a number only. So how can I convert, if I want to find out the apple out of this particular network, then how can I get that? Because my network can only output numbers. So we need an encoding scheme. Let me tell that, let me say that cat is 1, dog is 2, bus is 3, plant is 4, and it is 5. And what does it essentially mean? That I say that 001 is cat, 010 is dog, 011 is bus, 100 is plant, 101 is apple. This kind of thing, that actually, because if you want to output a number, you have to output as a binary. So this is what you are going to say with respect to them. Okay, so this is we can say that we have done a kind of encoding. So in this encoding, how many output neurons are needed? Okay, can anybody tell how many output neurons are needed in this kind of encoding? Can you type 1, 2, 3, 4, 5? How many neurons you need? Okay, 3, because if it is a cat, it is going to, from here you, what you get an output, you get 001. If it is a bus, 011. If you get 101, it means it's an apple. So 3 bits are sufficient, means 3 neurons are sufficient to be placed at the output place. Ultimately, what we have talked about, that this is going to be a neural network circuit, and out of that you are going to get these as output. Okay.
But we can
So
also like do, sir, added how?
please ask.
So we can also still have 5 neurons in the output layer, which each indicates one of these categories, right?
Okay, wait.
So
Okay, please wait. These things are
okay,
going
sir.
to come. Okay. So is it fine till now? Okay. So we will discuss this. Okay. So this is one kind of encoding. So another kind of encoding, as Mohit is suggesting, could be this, that there could be a second kind of coding which says that I use 10000, means I can say that in the it is going to be a 5-bit number. It is going to be a 5-bit number where I say that if first bit is 1 means it is a cat, second bit is 1 it is a dog, third bit is 1 is equal to it is a bus, otherwise it is a plant or apple. So this is a new kind of encoding. So early, a few minutes back we have seen the encoding was 001 010 011, and now I'm telling that this is the another kind of encoding. This is the second kind of encoding for the same item. This kind of encoding is called the one hot encoding. It has a name called one hot encoding. So if I ask you that which one is better, so let us try to evaluate that which one is better. Okay, whether we should use this first one or second one. You can by yourself see and tell, sir, here only I need 3 bits space, but here I need 5 bits to be output. So what happens that if you increase the things over here, if 5 bits you want to take the output, so network become more complex, because you know that the for everything need to be fully connected with the previous one. So network need more complex network. So it is not a good idea, because having 5 thing is not good idea. What do you think? It comes in your mind that if you want to use 5-bit, is it a good idea? If you can reduce the space, what's the problem? It is better to use 3-bit as compared to the 5-bit. So let us try to evaluate our this understanding. So from here, let's assume that I'm going to use this kind of encoding, and I want to find out that what is the average of cat and bus. So what is cat? Cat is 001. What is bus? Bus is, you know, that 011. If you add these numbers become 1, I think it is 001. This is the number. If you take half of this particular number, it becomes 010. Okay, half of this particular number becomes 010. What is 010? If you just try to see that what is 010, it is going to be dog. Okay, so what does it mean? That cat and plus bus divided by 2 is equal to dog. What is this? Do you see that? Is there any kind of real relationship? It is it a real relationship? Because all these choices were arbitrary. Instead of dog, if I have given this code to, for example, if I given this code because I was arbitrarily assigning, I can assign this to plant also. So it may be possible that the cat and bus, instead of dog, it is going to be plant. So is there any means logical reason that why it is happening in my thing? It is only happening because I have chosen this kind of representation. So it looks like that here comes the first alarm. That looks like that there is some problem. Do you see the problem? That there is no semantic relationship, but by having this kind of code, actually we have developed a kind of relationship between these items. So this is the first problem that we have. Now also let us find out that what is the similarity between two items. Okay, if we pick cat and dog, for example, what is the similarity between cat and dog? You see that similarly, ultimately you are going to apply the functions. So what is cat? Cat is cat is 001. What is dog? Dog is 010. So if you want to find out the similarity, so you can see that there is no similarity, because you can see that into the every bit this location 0, so there is 0, because most of the time we have the sparse representation. So 0 we don't take care. We just wanted to understand that at how many places this is giving some information, and also the same other thing also have the information. So 1 and it is when the dog is 1, then at that bit position cat is 0, so we have nothing. Similarly, second one, when the cat is 1, then the dog is 0, so there is no similarity into this particular case. But however, if we want to find out the similarity between cat and bus, so cat is 001 and bus is 011. So you can see that there is one place where you can find out that there is a similarity. So what is the similarity score? It is 1. Do you also see that is there such any kind of this kind of behavior also exists in your real representation? So is there any similarity between cat and bus? Is there any big? They should not be, because when you are going to represent the different categories, means what? They are orthogonal. You say that these are orthogonal. So apple and plant are not same. When you are going to make the number of you say that number of categories are 5, then it means that this category is not the same as the previous one. So there should be always 0. How come the 1 is coming? Okay. And sometimes it may be also possible that few items have the similarity 1 and another item has the similarity 2 and some items are in similarity 0. What does it mean? It is not the relationship that we wanted to establish. So again, this is again a big again a new kind of problem where we are actually stuck. So this is again because of this representation only, this kind of thing is coming to us. Another thing that actually I want to emphasize is this, that try to see that what is the loss for respect to the plant and apple. So what do I mean by this? Actually, just consider that you have a neural network circuit, and at the neural network circuit you have three neurons that are going to be treated as an output. So when I'm going to show an image to this particular network, when I'm going to show a image to this particular network, so to get the, for example, if I want to find out the plant, it should be 100. If I want apple, it should be 101. Okay. So if I want to do a training, so I would be only focusing, in the case of plant, I would be focusing on this bit because I want this bit to be high. However, in case of the apple, I want 2 bits to be high. I want here and here high. So in the complete circuit, I would do the changes in such a way so that more changes are going to happen with respect to the apple as compared to the plant. Because if I want to do the changes into the network, I want to adjust the weights. So weights are going to be more adjusted when I'm going to feed the apple into the system. And with respect to the plant, the changes are going to be less because I am going to focus on this particular part. Again, what does it mean? That this kind of representation actually gives to some of the classes, it gives more focus. All these things are bad because these properties don't exist in my data. So how can I represent this into some uh, other representation, the same thing, and I bring more relationship between them, so that this means that it is not a good kind of representation. So we call it the ordinal relationship, means there is some order. When we say that cat is actually cat is smaller than the dog, a dog is smaller than the bus is smaller than the plant is smaller than the apple. So this relationship should not be present in our representation. Okay, we don't want this kind of representation. Similarity between the classes to be avoided, and for example, if we find out that there is any similarity between them, this is not a good thing. So they should be orthogonal. How can I make them orthogonal? Means whatever vector representation cat, dog, bus, plant and apple have, what we need, that their representation should be orthogonal. There should not be any similarity between any pair of those items. So if we put the vector into this particular format, for example, if I say that, let's assume that this dog and plant, try to find out what is the similarity between these things. So you can find out that cos theta is equal to, so you can say that representation of C multiplied by representation of plant divided by, that how can you find out that what is the C multiplied by P. Okay, here you see that if you find out the dot product, so term by term dot product is always going to be 0 for all the pairs, if you see. So therefore this representation has also this kind of representation. When you are going to represent them as a one hot, it also has this particular property. Large loss should not favor a particular class. So this is also going to be the same thing, because everywhere only one place there is one. So it is not going to be that in when you are training a particular class, sometime you are going to have two ones and sometime you are going to have only one. So this, by this you are also going to ensure that loss is not favoring to any particular class. So that's why we go for the one hot encoding. That this is a very important topic. Okay, please try to understand. Any questions you have? Do you understand this? Mohit, your doubt is
Yes, sir.
clear?
Yes, sir. Yes, sir.
Yeah. Okay, so I want to bring this definition that was actually given by Yoon Lee Kun, who is a very known person in our deep learning community. So he actually says what is deep learning? About the deep learning, he gives this particular definition. And this definition I want to bring in front of you because what is deep learning? Many of the time people are asking to you, so you should give this definition. Very good definition it is. There's I came across this definition. I must tell you. So deep learning is constructing network. What is deep learning? You are going to construct network. And when I say the network means definitely I'm going to talk about the neural networks. Okay. So you are going to construct network of parameterized functions, network of parameterized functions, functional modules. What do I mean by parameterized function? So for example, if I say that sin x, okay, sin x, you know that there is a behavior of the sin x. You know that this function can be parameterized by writing that sine of ax plus b. The better function, the better representation of the sin x could be this, where you are saying that there is an amplitude, there is a frequency, and there is some what is called that there is a shift, initial shift. So you know that this is a kind of function, and if you want to plot it, it is going to be some sinusoidal kind of function. But if I change the value of a, this small a and small b, it could be a different function. So different kind of functions can be made using this a single equation. And what I'm changing over here, I'm changing the parameters. So this is a function. So I'm going to make some. I am going to this particular system with that I'm going to make is going to deploy the functional modules uh, that are parameterized, and we are going to find out using the training that what are the right parameter. We are training them using example, so we actually don't solve any mathematical problem. When we formulate this particular thing, we show the example to the system, and by this we try to find out that what are the right parameter using gradient based optimization. So how can we do that? By showing the example, how can we proceed? So we are going to apply the gradient based methods to the system to find out the right parameter. Is it clear? So you must understand a very important part from this particular definition. So let me give you some idea. So right now, let me tell you this. Let's assume that you have an image, and okay, and you want to find out whether there exists a cat or dog. Let me try to be very good. Okay, so anybody like this cat? So let's assume that I develop a system. I want to make a system where I wanted to tell whether there exists cat or dog into the system. So how can I go ahead with the into the general pipeline? Means what are the general things that you actually want to do? The first thing after capturing this image is going to be that you want to enhance this image. Enhancement can also be taken as that, for example, you want to resize and you want to improve the contrast. If it is a low lighting condition, you sometime apply the histogram normalization and other techniques. You want to enhance this image. After enhancement, after enhancing this image, you find out where is the region of interest, because it could be a big image and cat could be here, cat could be here, cat could be anywhere. So where is the cat? You have to find out this. So for that, you have to find out where is the region of interest, ROI. So sometime you can apply some attention based mechanism that can tell that this is the area that looks to me that is an interesting area. Then after that, you extract some kind of feature. Okay, you extract feature. So what are the feature that make a cat different than the dog? Okay, so for example, if I want to find out that the difference between a elephant and say if I want to differentiate between elephant and human, so I say that elephant had tusk, elephant has 4 legs, human has only 2 legs. Okay, I want to find out these kind of features. So the feature are going to be dependent on the problem. So I ultimately have to find out some feature that differentiate these two categories. So I do a feature extraction, and after the feature extraction, I have to apply some kind of classification framework. Okay, then I get the decision that what is over there. So all these things should also be done by your network also. You must understand that if you are going to make a deep learning based system for this particular problem, so these things should also be there in your system. What do I mean by this? I wanted to say that given an image, there should be some functional unit that neural network functional units that are going to perform, that are performing enhancement. There should be some unit, next unit, that is finding out the attention, region of interest, next functional unit that actually try to do feature extraction, next functional unit that try to find out a classification, and then there should be a decision part. All these things from outside would look like to you that okay, I have just put everything as a densely connected neural network, but no, it is not like that. There are multiple components which are into the system. When you feed this thing to the system, you are going to get the output. Inside there are multiple functional units that are going to solve your particular problem. Make sense? If you understand this part, you must also ask that, sir, how can we decide that what how many things would be there into the enhancement, how many things would be there into the uh, attention and ROI, all these things. How can I find out this? So for that you need some kind of experience, that if you have done this thing using you just solve this particular problem sometime, and then using different kind of network architecture, then you come up that looks like that this is going to solve this particular problem. This kind of architecture is better for this particular kind of problem, and then you deploy the right kind of things over there. you would you definitely have to answer many questions, such as how many layers are required, how many units in each layer, what should be the learning rate, how to initialize the parameter, what is the right activation function. All these things you have to find out to actually solve this deep learning problem. So any kind of problem need to solve all these things from your end. Any questions on that? So if you want to, again, I have raised a question that you have to answer these questions. How can you answer this question? Again, very difficult to tell. The general way to answer this kind of question is this, that you have to get some experience. Okay, you cannot say that I don't know anything and you are going to develop a very good system. So you need an experience. So how can you gain the experience? You start by doing wrong things, then after that you see that you get a feedback that things are not working, then you modify the things and go ahead with that. So the same idea is this, that you get inspired, but you are thinking that okay, even if I don't know, looks like let me go to the neural network and apply 2 layers. Then you code and implement and build these things, train the system and evaluate, find out that what how good this particular system is. You find out okay, no, this time the system is not that good. Then you again go and get some inspiration. Looks like that what should I do if I increase the number of things, if I increase the number of things, or what should I do? So maybe you increase the number of neurons in some layers, or number of layer you are going to increase, or you are going to connect them in a radical way. All these things you are going to do. Once again, whenever I say that you are going to get the inspiration, this inspiration is always coming from where? Philosophy. And there is no guiding principle for that. You have to radically think something out of box and then get the inspiration, and then you can apply over there. And after some time, after multiple iteration, when you do the multiple sufficient number of iteration, you would be actually at the place where you would be better. So it is not very difficult to see that. Let's assume that your accuracy is this. So definitely when you are going to change, it could be possible that accuracy is going to be down or even more down, but there could be some method that can improve your accuracy. When you got something that it is going to improve the thing, you are not going to report this thing. You can tell that okay, I start by this, then I did this thing. In every paper you only report the things which are actually going to give you the success, and by this, as the time progresses, you are only going to get the better and better systems with you. So where is the knob? Means where what are the things that actually you should change? Okay, based on what criteria you should change? So the first and foremost criteria is the underfitting and overfitting. Okay, you see that how much your system is, whether your system is underfitting or overfitting, and based on that you can do it. So what is overfitting and what is underfitting? What is underfitting and what is overfitting? Okay, so you know that you train, there is train data on this, you train the things, and after that you test. Okay, on the test data you want to test the system, you want to be better into the test thing. Definitely you want to be better, but sometimes it may be possible that you are bad in the training and you are bad into the testing also. Sometimes it is possible that you are good into the training, but you are bad on the testing. So your model is learning very good on the data that you have, but you are bad when you are going to test this. This particular condition is a problematic thing called overfitting. However, if you are bad on the training also and testing also, this is called the underfitting. So if you are doing underfitting means what? Your system is not doing well. You are doing underfitting means what? Your system is not doing well. So how can you improve it? Definitely, you should increase the power. Increase the power. By what? How can you increase the power? So if the number of layers are there, you can increase the number of layer. Okay. If or you can in the same layer you can put more number of neurons. You can increase the number of neurons over there. So if you are underfitting, what you could do, what you can do, you can increase the power. Okay. And if you are overfitting, what you should do? Overfitting means your system is now good, but it is not good on the test data. So there could be two approaches. Either you simplify your model by apply some kind of regularization, or next part could be, that is very interesting to see, that sometime you put some test data into the train data, because system is bad. Where the system is bad? System is bad into the test data. So use that test data to train. Ultimately, what would happen? Uh, so what I was telling that, don't take it wrong. Okay, so let's assume that this is what the data you have. You have divided into the training and test part. So on the training data, your accuracy, you are overfitting means training here your accuracy was good, but here in the test data your accuracy was wrong. So I'm telling that you take few items from here and put it here. So by this what would happen? That this training is going to be increased, but don't show some example you must retain. Don't show these examples. Okay, don't show all the examples. Okay, put more things, and it also mandates that put more data. Okay, so you are also adding some data points, and maybe what does it mean? That you increase the test thing and put more data for the training. Ultimately, what I wanted to tell, that put more data into the training. Make sense? So what would happen that if you put more data? So, so now right now my assumption is this, that my system is learning good. So if you put more data over there, so it would become good on the things for which it was earlier bad. Because on this data it was bad, na? If I show this thing to my system becomes good on this data also. So ultimately my system is going to be better. So this is called the overfit. This is called the overfitting, and how you fight with that. Make sense? Okay. Now I wanted to discuss something about the that how you should initialize your weight. In weight initialization is very important. So let me give you some idea that what is why we should need a kind of good weight initialization. Just consider that you have a neural network. Okay, you have a neural network. You are providing some feedback to that particular system. You are going to provide some input to this particular system, and try to see that what is the output. Based on the output you are going to take the decision. So let's assume the case when the weights are too small. When the weights are too small, so weight could be what? Weight could be 0.01 if weights are very small. If the weights are very small, so whatever input you are going to give, they are multiplied by this, because ultimately they are going to be multiplied, and after that there is some activation is also proportional to whatever value you are going to get. So the output that you are actually earlier having, if I reduce the weights, you are going to get the output. The output would be have the smaller value. Make sense? So if the smaller value is here, and it is again this weight is also small, it becomes a smaller. It becomes here also weights are smaller, it becomes even smaller, even smaller, even smaller, even smaller. So ultimately what happens, the output that you are going to get is going to be, you are going to get the very small output. If the weights are very small, you are going to get the very small output. Okay. If the weight is high, so for example, if it is a 5.5 something, big value, so every time the value is going to be multiplied by big weights, and after that you are going to get a very high value. Okay, so because multiple layers are there, so if you multiply this, your weight becomes very high. So what is the problem with this thing? That if you get large weight and small weight, actually what happens now at the end, at the final weight, at the final place, you are going to utilize some kind of activation functions to find out the right kind of thing. So activation function, so let's just evaluate one of the activation function, sigmoid activation function. So what would happen that if your weights are very small, if your weights are very small, so output becomes very small. Very small values go into the activation in this sigmoid thing in as an input. So whatever output you are going to get, it is also going to be very small. So you are actually operating into this particular area. If the weight are small, you are operating into this particular area. If the weights are large, you are operating into this particular area. Is it clear to everybody? Because into the sigmoid, if you want to see that what is the output actually you are going to get, because you are going to apply a activation function, then you are going to get the output. So your output would be either here or either here. Okay, makes sense? Because the value is higher or lesser, so you'd be getting the value over here and here only. So what is the problem with this kind of thing? The most problematic thing is this, that if here the gradient is very small, here what is there? Gradient is very small. So if the gradient is very small, what does it mean? That because if you want to learn something, you have to modify this weight. There is a weight to which you want to modify to get the correct weights. And if the gradient is very small, means this weight is going to change very less. So whether you would be easily able to find out the right weights at this particular place. Either you are here or here, both the cases, when the weights are small and large, in both the cases, your operating point is actually such that your weights are not going to get updated. So your system is actually learning very slow, and therefore you would not be able to train the system in an efficient way. Make sense? Make sense? So if you look, I don't care. Look, once again, I don't take me wrong in this particular way, that if the weights are small or large, I don't care about this. If it is final weights, if my system is fully learned, let's assume that I have done something by this, my system has fully learned. I don't care whether the value is high or large. But at the time when I am going to start my system, at that time weight should not be that it is very high or very large and the things are not changing, because now I don't know that whatever value I'm going to provide to my neurons, they are wrong. We expect that they are wrong. They are going to be they are going to change in such a way so that at the end I'm going to get the final thing, the right thing. But because of this kind of setting, I would not be able to get the right thing, because my gradient is very small, my system is going to learn very less. Understand? So this is a pretty big problem. Any questions on that? Anybody want to
Sir,
say?
if weights are large, then wouldn't it be operating in the region which is shown?
Weights are large, then output you would be
Sir,
getting
even
large.
if right,
Hmm? You would be
sir,
here.
yes, sir, if weights are large, yes.
Okay, then if the weights are large, you would be working in this particular area. Weight are
Ye-
smaller, then you would be working in this area. In both the area, what is the gradient of this particular function?
Very less.
Gradient is very less. So ultimately the change that you are going to get is going to be very less. So you are not able to train this particular system. Initially you want to train the system, so that's why you cannot put this value. However, once again, see this, if you want to be better, you should be into this particular place, in this particular place where the gradient is high. But again, I wanted to tell you that this particular area is also very problematic, because what happens now, here the things are linear. Actually, here the things are linear. You also don't want to, definitely want to be into this particular region, because having this region actually says that things are linear. Linear means what? You have seen that if the things behave, if your activation function behaves as a linear, what happens, that everything collapses to a single model. So this is also a problematic. The direct this particular means, if you go this particular way, very narrow range, this is also not very good. You should be somewhere here and here. How can we be here? We try to understand. So first try to understand this part, that instead of being here and here, I want to be here. I'm telling one more thing, this you must take into care. But right now I'm not talking about just now that this how to solve this particular problem, because what happened now, if you are here but some activation is there, some things should be So I would come back to you once again. So I just wanted to tell this thing that at this particular moment, everything looks like that it is a straight line. So sometimes this also brings a bad thing that your network collapses to a very simplified thing. But that is fine because initially, if you start learning in this particular way and then the weights adjusted in such a way so that either you move here or here, then your learning would be appropriate. I think this you must understand. Okay. All right. So what we want the variance of the input and output should not differ much, at least initially they should not very different, because if initially they are going to be different, then we would be into a big problem. So I have what so ultimately what we understood, that if we have a network, can I ask this question, then can I put all these values to be zero, all these two values to be zero or same? Can I put all the values to be same?
No,
The
sir.
answer is no, because if I put all the things to be same, what is going to happen? That for example, if there are two neurons here and here, so the same changes that is going to be here would be done into second one also. So they are everywhere. They are going to do a march past. Okay, all the values are going to be changed into the same way. So ultimately, a wrong kind of ecosystem we would build, and the system would not be able to learn. So one method is this, that you randomly initialize the W's, but this is not a good strategy, as we have discussed, that it can most probably going to lead to exploding and vanishing gradient. Am I right? If you are going to develop this network and you are going to initialize this weights randomly, so most probably they are going to do exploding and vanishing gradient. So this is not a good strategy. Next strategy could be initialize with the zero weight. All the things you initialize with the zero weights. Is it a good strategy? Again, it is not. A few minutes back we have talked about that uh, uh, all the neurons in a particular in the same layer, they are going to be updated into the same way. So it is again going to be not going to work for me. The next strategy that I'm going to talk is called the Xavier weight initialization, and this is this is a very good strategy, and most of the time we use this strategy in our system. This is called the Xavier weight initialization. What is this method? This method says that that what is the operating point that you actually want. You want something nearby zero. Okay, so it says that it actually says that is standard that you actually uh, you on the zero you fit a Gaussian on this particular place, means you actually want to be weights to be distributed around this particular value only. The same value you cannot give, so you somehow want to do a sampling. And how can you do the sampling? That why I'm telling the Gaussian, that most of the real life phenomena that we actually encounter, they are actually Gaussian. Okay, if you measure that what is the height of the student in your college, try to see, so it is going to be Gaussian. If you see that how many marks the students are getting, it is again going to be a kind of Gaussian. So Gaussian is a fundamental thing that most of the time we observe the thing. So all the fundamental samplings are going to be like that. So most of the time we say that we are also going to follow this sampling from the Gaussian. So if there is a Gaussian, so there are two properties that we say, that what is mean and variance. So mean is actually we want to be centered around zero, because we don't want to give anything to be higher weight, and then we are going to sample around this. We don't want to give things. So this means what? That probability of getting a point here is very high as compared to the point that I'm going to put as I'm going to pick this particular thing. That this is a standard method to do that. So what we want this standard is to make weights center around zero with a small variance, and the variance is going to be k upon SL minus 1. What is SL minus 1? So let's assume that I have a layer, I have a neural network, and you are on to the layer number L. So any neuron, if you pick over here, it is going to be connected. How many of them? Previous SL minus 1, because if this is, let's assume that is the first layer, this is the second layer. So if you are going to be on the layer number L, every neuron is going to be connected to SL minus 1 number of other neuron, because we have the fully connected circuit. So with this understanding, You understand that what is this particular value? K divided by SL minus 1. Okay, this is what the variance is. What is K here? K is actually selected as a heuristic in in this Xavier initialization, and it is 2 for ReLU, and it is 2 for ReLU and 1 for sigmoid or tan H kind of activation function. So based on your activation function, they have actually, there was a paper that actually talks about this, that it would be better that if you use K is equal to 1 and 2 for the ReLU. This kind of initialization method is called the Xavier initialization. Any questions on that? This thing is called the Xavier initialization. This has a name called Xavier initialization. Here, when I was using this, instead of, there are a few more possibilities are there, such as, because you know that if SL, it has SL, if you are into the level SL, and here is SL minus 1 number of things are there. But however, how many neurons are there? SL number of layers. Let's assume that SL number of layers, SL number of neurons are there. So SL multiplied by SL minus 1 number of values actually you have. So sometimes you can say that K divided by SL minus 1 into SL, because you distribute all these different values, or you can say that SL plus SL. All these things are possible. So multiple, it depends upon your problem. Sometimes you change these values and see that which actually works well for you. But the basic idea is this, that you are going to have some small variance. The only idea is this, the basic idea is this, that you are going to make the thing centered around 0, and you are going to define a kind of variance, and with that variance you are going to pick the particular item. For the initial training, you know that when you are going to find out that what is the activation from this particular neuron, if this value is very high, sometimes it may be possible when you are going to, because of this multiple effects, initially this value is very high. Say, let's assume that you define a threshold, that higher threshold is 2.5, and low threshold, it could not be 0.5, it could be, for example, 0.9. Low threshold is 0.1. So if this output becomes greater than 0.9, you pick 0.9 only. If it becomes less than 0.1, you take 0.1 only. For initial few iterations, you can use this method also. This is called the gradient clipping. Okay, let us see some mathematics behind this, that why we are using this. So what I was telling, that you have multiple layers, and for a particular neuron you want to find out what should be the weight, what should be this initial weight that I wanted to find out. So I can safely assume that all the weights that you are going to apply over here, they are taken independently. They are means independently and identically distributed samplings you can find out. For example, I say that there is a distribution where mu is equal to 0, and sigma is equal to 1. How come sigma is equal to 1? Because we have seen that anytime you can do some kind of uh, scaling and translation, you can always perform on the data, and that did not affect any kind of the nature of the classification of your problem. So we can always safely assume that your mu is equal to 0 and sigma is equal to 1, and all the weights that are actually taken, they are taken independently. They are taken from this particular distribution independently. All these values are got by this. So you know that in the mathematics, you know that if you it is generally coming from directly from the statistics, that if you want to find out that what is the variance of two variables. So because weights, there are two things. One is the weight and another is the x. If you want to find out what is the variance of all these things. So I would not go into the detail of the proof of this thing. You know that variance of two things when they are multiplied is going to be expected value of xi square plus variance of wi, expected value of wi square plus variance of xi, and multiplication of variance of xi and variance of wi. We have told you that if whenever a data points are given to you, you can always transform this without any loss of generality. You can always you can take it and you can transform it. You can take it smaller, you can take it here and there. By this you can always make what, that mu is equal to 0 and sigma is equal to 1. So if you can do that, so expected value of x square can be made to the 0, and expected value of w is also going to be 0, because we have, let's assume that we have transformed them and these values has become 0. Without loss of generality, we can assume this thing. So in this kind of setting, the special setting in which we are, where we have actually changed our data, what we can say? We can say that if variance of the w and to xi, if we want to compute, we can compute using this particular formula, that variance of xi into variance of wi. Okay. Let us see one another very important property, that any very important variable. For example, if you want to find out that what is the output, if you want to find out what is the output of a thing, so output is going to be, you know, that wixi plus w2x, sorry what I want, what I'm telling, w1x1 plus w2x2 plus wnxn plus b. You know that this is what the output is. Okay, because if you have a perceptron and some input you are going to provide and you are going to get the output, so this is what the equation you have. So activation, I'm not putting activation right now here, because we, you know, that we are, let's assume that we are actually operating on this particular place, and if you are operating on this particular place, say, then it is going to be mostly output is going to be the same as the input. Okay, so if this is y that I have, so if I want to find out that what is the variance of y, variance of y can be represented by the variance of this term, variance of this term, variance of this term, individual term, this formula. Then this particular variance would go inside, because there is a summation term, so you want to find out the variance of individual terms. About the bias, bias is a fixed term, so variance of bias is going to be 0. Okay, all these w's are also going to be taken using the same kind of, because of IID, so you can say that it is a variance of wi some value. So all these things are going to be the same. Similarly, if you want to find out what is the variance of x1, x2, xc, they can also be told as the variance of a single xi. You can tell them they are also going to be the same, because we can say that they are also collected into the same way. So this value becomes 0, variance of b becomes 0, and here all these values become same. Once again, how many values we have? How many values we have? How many values we have? So if I was working on a network and I was on this layer L, so SL minus 1 things are there into the previous thing, because these things are coming to me to give me, to take me out, take my output. So how many values were there? SL minus 1. So this summation can be written as what? This summation can be written as SL minus 1, SL minus 1 multiplied by variance of Wi into variance of Xi. I can write like this. This is going to be this variance of y. Here again, we have to see something, that let's assume that you have a big neural network out of that, and you are providing some input to that. Okay, y, x, sorry, you are going to provide some input to the system. Okay, you are going to provide some input to the system, and by this you are going to get some output. Try to understand that if here is some variance into the system, the same variance should also be there into the output. Otherwise you are actually missing something that is going to, that you are providing into the system. Whatever your output is there, it is going to be dependent into this, must be dependent in the system in such a way, so the same variance it should also have. Okay, because it cannot introduce anything, your network cannot introduce anything new, the same thing should come out of the system. Okay, if the same thing should be there, what do I mean by this? That if you have made a right system, then this value, that is the variance of input and variance of output, they should be same. If they should be same, so I can say that SL minus 1 into variance of Wi is equal to 1. So I can say that variance of Wi is equal to 1 upon SL minus 1. I can say like this. And this is the same formula that we actually have written over here, that it is k upon SL minus 1. Okay. So this is the basis of this Xavier initialization, that actually talks about that since this value is equal to this value, so this complete thing has the value is equal to 1, or we can say that variance is equal to 1 upon S L minus 1. So using this method, we actually initialize the thing to find out the right parameter. Thank you very much.